In the previous video, we looked at the idea behind electromagnetic waves and how Maxwell sort of figured some things out about how that electric fields work, magnetic fields work, and we connected them to light. So now we're going to take those ideas, we're going to keep on going a little bit, and I'm going to put the sheet on your class website so you can just print off a copy of it, but we'll just go along, we'll go through a few things, that type of stuff, okay? So we're going to go beyond Maxwell a little bit. And first of all, the idea of continuous self-propagating electromagnetic waves was a very big deal in the 1850s, 1860s. So really, really huge. And this is what we talked about last time in the previous video, that light comes from charges going and oscillating and moving, creating the changing electric fields, magnetic fields, etc., and they keep on going and keep on creating each other. And whether it's at the atomic level or whatever else it is, it doesn't make any difference. This is where light comes from. And when they started looking at this, they started looking at the spectrum. You guys know about the light spectrum, the electromagnetic spectrum, and they started looking at that and finding all these different types of radiation, these different types of light with their different frequencies and wavelengths, but all having the same speed. So all these things were kind of cool, all sort of coming together because of this. And these are what are called black bodies. Now, if you're not sure what a black body is, basically a black body is a perfect absorber of radiation, but you can also talk about black bodies being like perfect emitters of radiation and that type of thing. So we're going to look at black bodies first a little bit, sort of show you how that works. Okay, so a little bit about black bodies and how black bodies work. So here's a picture of, well, it's a made-up picture, but it's a made-up picture of the same room being lit up by 8 different lights at 8 different temperatures. We've got all the way starting at 550 kelvins all the way to 6500 kelvins. And you can see as the light gets brighter, it starts with a reddish type color and then gets like orangey. But as the light gets hotter and hotter and hotter, you start seeing a broader range of colors between the red and the green and the blacks and grays and all that kind of stuff becoming better. And that's the idea behind radiation from objects, that depending on the temperature of the object, different objects will give off different ranges of colors. So when it's at 550, there's like no greens really being given off that you can actually pick up on, so you can't see the green. So as the temperature increases, you get a bigger spectrum of color available. So the basic idea is something like this, where when you have something that's colder, it's got a very, very small range, like the 200 Kelvin little dark red blob. And as things get hotter, you get a much bigger range of colors being given off in a predictable distribution. And the sun, of course, the surface of the sun is around 6,000 Kelvin, so that's why this one maxes out there. And you see lots of different wavelengths, lots of different colors actually being given off. Okay, so in laboratories and stuff like that, they'll use little devices called black bodies, which are basically light goes in. It's basically a hole, light goes in, light gets trapped, and so things looks black. So like your eye, like the pupils of your eye are literally black bodies. That's why they look black, because the light goes in, gets absorbed, it doesn't reflect back. Unless it's like from the flash of a camera, then some of it reflects back and you get the red eye type effect. But basically anything that absorbs radiation in colors is a black body. So like a black hole, of course, is the perfect ultimate black body because no radiation can escape from it. So that's the idea behind it. So I'll show you another little picture here. There you go, another distribution type picture where different temperatures give off different colors in different amounts. So this is the basic idea behind black body radiation. Black bodies are these perfect emitters of radiation. They give these nice distributions depending on their temperatures, really predictable. It works really, really, really well. Okay, so that's the basic idea behind black bodies, and we'll come back to this in a second. I want to show you, go back to what we were doing before. So that's what they're using black bodies for. So black bodies were used to emit radiation or absorb radiation, and they could analyze the frequencies that are being given off. Because you can also have black body like emitters where you heat them up and they glow and they give off frequencies. So black bodies can absorb or emit. Sometimes ones that emit are called white bodies instead, but whatever. The thing is, when they analyzed the frequencies, those distributions that actually were coming off them, Maxwell's equations didn't work very well. They couldn't really actually describe the distributions of frequencies given off by things that were heated. Sort of like, a light bulb is heated to give off different frequencies. Couldn't really explain the distribution. So some people came along to try and figure this out. Now, 2 guys, Rayleigh and Jeans, it's probably Jeans or something like that, but whatever. They used classical physics to try and solve it, but they couldn't really explain the higher frequencies, and sometimes referred to as the ultraviolet catastrophe, a little dramatic, but whatever. Then another guy came along, Wiens came along, and he was able to do the opposite. He was able to explain the higher stuff, but the lower frequency stuff didn't work very well. So sometimes called infrared catastrophe. But then another guy you may have heard of came along. Max Planck came along. He'd actually worked with Queens, and he actually combined the ideas together in order to try and figure out how this actually worked and what was actually going on. So then in 1900, Planck announced he had a brand new formula to fully explain black body electromagnetic radiation distributions. But the problem is it was based on something really, really strange that people were having a little bit of problems with. He said, first of all, that energy flow or the energy coming from light was not smooth. It actually came in packets. Now, this caused a problem because right now everybody thinks that light is acting like a wave, and waves are smooth and have smooth energy transfer. And he's like, no, the energy flow is not actually smooth, but the energy actually comes in little tiny packets. And every single oscillation from a charge, every time it wiggles up and down, it gives off a distinct quantized amount of energy, not a random amount, not any amount you want, it's quantized. So the amount of energy you get, the total energy you have, is an integer number multiplied by the energy per oscillation. So you can't just have whatever you want. It's sort of like if you only have $5 bills. If you only have $5 bills, you can't have $7, you can't have $8, you can't have $11. You have to have 5 or 10 or 15 or 35. It has to be a multiple of the 5. And according to the wave people, you can have any number you want. And Max Planck goes, no, like you can't. It has to be quantized. It's chunked together. All right. And the third part is he said that the energy was directly proportional to the frequency of the light. And if you graph the energy and frequency, you get a nice linear graph, really, really simple. So you get a basic slope, and the slope is Planck's constant, which is 6.626 negative 34 joule seconds. So this is the things that he came up for Planck's hypothesis. And of course, it really threw people off because he quantized the energy. And he said, no, it's not a smooth flow. It's not any amount you want, which is very much a wave idea. He said, no, there's chunks of energy. It's quantized energy, which is very much a particle idea. So this really threw a lot of people off. So after almost like 100 years of wave model dominance in terms of how light works, the particle of light idea was back. So of course, Max was really excited about this. Of course, a lot of people involved with light were very upset about this because this is not exactly what they had planned on. Now, of course, it's one idea to actually predict this and theorize, and another thing to prove it. So if you go back to the black body thing that we were looking at before, and I think I'm going to give you guys the sheet on your class website too. They said, fine, let's test it. So they did a test where they said, okay, we'll experimentally check some distributions, and you predict what they are using the Maxwell's equations and Maxwell's ideas and see what actually happens. And when they actually did that, they got something that looks like this. So the theoretical part, where what Max Planck predicted is the curve, and what they actually collected in the experiment of the dots, and you can see there's a definite correlation between the two. So just with this alone, it definitely showed that Max Planck was onto something, and there was definitely some kind of particle attribute thing going with light. It wasn't just this easy wave thing going on. So it was a really, really, really big deal. And again, having the experimental backing for it is a huge thing. So it wasn't just a theory. There's actual experimental backing to go along with it. Okay. So again, go back to this. It's really important, that frequency was directly connected to energy. There's definitely this particle, this non-smooth energy transfer. There's these chunks of energy coming in. And this is where the photon idea comes in. You guys probably heard of photons before, and that's where this really kicks in. So this is about, just about 120 years ago is when this is really kicking around. And during this time, this is when, the electron had just been discovered and verified as a particle and that type of stuff. All the things, basic atomic structure are kicking in. And this is all around that time. So a really, really exciting time for the mega nerds out there and all these things tying together. Okay, so let's look a little bit more about how this idea works and show you how the Max Planck calculation kicks in, because it's actually pretty simple. So let's show you how to do the basic calculations. It's actually really, really simple. It's not really difficult at all. So the basic expression we have is energy is equal to HF, because we had an energy frequency, the graph, something like this, and the the slope was the Planck's constant, which is h, and it goes to the y-intercept because, you know, zero frequency, zero energy. So it's just this really, really, really simple little expression. And of course, h was 6.626 times 10 to the negative 34. So it's actually really easy to calculate the energy of whatever type of light you want. Now, of course, the frequency is in there, and you know, a basic way to calculate frequency, of course, is frequency is equal to speed divided by a wavelength. So what you'll often see is this version is really, really common, but sometimes people will substitute in for frequency and put in the C over lambda for frequency, and it doesn't really matter. It's all the same thing. So energy is equal to HF, or energy is equal to HC over lambda. It doesn't make any difference. So let's take red. So if we take red light, and you guys know this, red light is, you know, usually around 700 nanometers maximum. So let's say 700 nanometer light, and I want to know what is the energy of that red light. Okay. All right, so energy red light. So there's two ways. We have the wavelength here, so I can just do the HC over lambda. So I've got the H, of course, that's my constant. That's my 6.626 negative 34. And I will multiply that by the speed of light, divide by the wavelength, and get the energy. So let's see, that would be around 2.84 times 10 to the negative 19 joules. So that is the energy of one red packet. Okay, so that would be one packet of red energy. So the idea behind Planck's hypothesis is it would be impossible to have, if you, like somebody said you got 3.2 times 10 to the negative 19 joules of red energy. That's not even possible. It has to be a multiple of the 2.84. So you can have the 2.84 times 10, that's fine, but then you have to times it by 2, times it by 3, times it by 4, times it by a billion. But you have to have a multiple of this. That is the only one that is actually possible. Okay, so that's the basic idea behind it. All right, so you have to have integer numbers of those. Okay, so let's do something similar. Let's use green. So let's say, what is the energy of, let's go with 5,000 green packets of energy. Okay, so what's the energy of 5,000 green packets of energy? Well, no problem here. The wavelength of green light, you guys probably remember this. You know, we're looking around the smaller wavelength, so we'll say around 520 nanometers for green light. So then all we have to do is energy is going to be, well, I got the lambda again, so let's use that, HC over lambda, and I can find the energy for one of them. And that'll give me about 3.82 times 10 to the negative 19 joules. Okay, now that's for one. So now I'm going to times that by 5,000. Okay, so I'm going to multiply that by 5,000 joules, or 5,000 packets or photons. So that would give me 1.91 times 10 to the negative 15 joules altogether. Okay, now you can see these energies are actually really, really, really small. So it's actually really common to use electron volts. So do you guys, guys did electron volts and that type of stuff in your field stuff. I showed that to you, and that's really common for that to be used here. If you remember, the conversion factor for that is 1.6 to the negative 19 joules. So if I take that 1.91 and I divide it by the 1.6 power of negative 19, we can get in electron volts, and this would be about 11,900 electron volts, or around, give or take, we're looking around 12,000 kilo electron volts. So this is why you'll often see electron volts with this subatomic type stuff. We can do the same thing for the one that we did first. We take that 2.84 negative 19 and divide by the 1.6 negative 19, and this one up here, this is looking around like 1.78 electron volts is what, not that guy, but this guy up here, that's that would be. So electron volts are really common for this type of thing. It's one of the huge applications for it. But again, if it's electron volts, you multiply by the 1.6 to put into the joules. If you have in joules and 1 electron volts, you just divide by the 1.6 negative 19, and that's it. But that's the basic way to calculate Planck's thing, chunked energy. So according to wave people, you could have any energy value you want, and Planck said that's not the way it works. And this is how you can calculate the energy of different photons, no matter what the wavelength is.